This video, we're going to be solving quadratic equations over the complex number system. And really what we're looking at is to determine what method we should use to solve the quadratic. So really at our disposal, we have a few methods we can use. We've got the factoring method, we've got reversing operations, and we've got the quadratic formula if nothing else works. We're not going to focus on completing the square. That is another method, but it's not one that we would frequently use. So we're not really going to spend a whole lot of time focusing on that. Uh, the quadratic formula is if we have an equation in this form, ax squared plus bx plus c equals 0. So in other words, everything is on one side of the equation, all of your terms that have actual numbers, and then a 0 on the other side. We can use the quadratic formula, which is this, to solve any quadratic equation. The challenge, though, is that in a lot of cases, it's going to be pretty messy. So we want to use that as a last resort because there's a lot of simplification that we need to do if we use it. So we want to look for other ways. But the cool part is this discriminant, this part underneath the radical, can actually kind of tell us what method we should probably potentially use to solve a quadratic equation. So if I get something that's a negative number, then I know that I'm going to get complex answers. So quadratic formula would definitely be an appropriate method to solve. If I get something that's a positive number, but it's not a perfect square, then the quadratic formula would also be something I want to use because I'm going to have irrational roots, something with a square root left over. But if I have a 0 or a perfect square for my discriminant, then factoring would probably be a more appropriate method to use to solve these equations. So let's go through the process here on, we're going to do 3 examples. I'm going to first start with number 7 here. I'm going to take away 8 from both sides to get it in the correct form that I could potentially use quadratic formula. So my next step is, once I've got it there, I'm going to find the discriminant by taking the opposite of b, I'm sorry, not the opposite of b, but b squared, negative 7 squared, minus 4 times a, which is 1, times c, which is negative 8. Negative 7 squared is 49, and this mess here becomes 32. And so that would give me 81. So that's a perfect square. What that tells me then is that um, quadratic was actually factorable. So I'm going to go ahead and look to factor. Because I don't have a coefficient in front of x squared, I'm really just looking for numbers that multiply to negative 8 and add up to negative 7. And so that would be minus 8 and plus 1. So those are my factors, which I'm then going to take, set equal to 0, and solve. And those are my 2 answers. So generally quadratics, we're going to get 2 answers. So let's take a look at one like number 9, where, oops, let me just stop inking and scroll. There we go. We're number 9, where maybe factoring won't work. So I'm going to take 3 away from both sides. X squared plus 2x plus 3 equals 0. All right, so first step I want to do is find the discriminant on this. So I'm going to take b squared again, 2 squared minus 4. A is 1, and c is 3. So when I go through the process, 2 squared is going to give me 4. This will become negative 12. Yes, it will, and I'll get negative 8 for my discriminant. So what that tells me is it was definitely not factorable because I've got that negative discriminant. So I'm likely going to have complex answers. So here's the cool part. If I've already found the discriminant and I determine that I need to use the quadratic formula, I've actually done the hard part already. So I can just basically take that and plug that in. So the quadratic formula says take the opposite of b. So I'm going to take the opposite of 2, which is negative 2, plus or minus the square root of the discriminant, which was negative 8, all over 2 times a, which is 2 times 1. Is 1. That gives me 2. I'm not done yet because I can do a little bit more simplification. So I'm looking at 8, and I know, first of all, it's negative. So I know that an imaginary number I is equal to the square root of negative 1. So I can basically take that negative out and turn that thing into an imaginary number. And then the 8, I'm trying to think about the 8 and what I can break it to. 8, I can break it to 4 and 2, 4 being a perfect square. So when I simplify that, I'm going to have negative 2 plus or minus, so the square root of 4 is 2. And then I've got the square root of 2 left over. And because of that negative, I'm going to really make that I, and then divided by 2. And so my next step is to look outside. Anything that's not inside the radical, I'm looking to see if they have something in common. And they do. They all have a 2, which I can then take that out. And so my final answer would be negative 1 plus or minus 2 divided by 2 is just 1. So I don't have to really write that 1 in there. And then technically be over 1, but I'm not going to write it because um, we just don't do that. So we got x equals negative 1 plus or minus the square root of 2i. Again, not factorable. The quadratic formula was a very appropriate method to use to solve. But on number 10, there's something structurally different about number 10 than the others. And it has to do with the fact that we don't have an x term. We have an x squared term, but we don't have that linear term at all. So if that happens, your strategy here should not be to factor or to use the quadratic formula. Your strategy should probably be to use reversing operations. So I'm just trying to think about x and what was done to that. First thing that was done to it was squared, and then I added 14, and that was equal to 11. So if I want to reverse it, the first thing I'm going to do is subtract 14 from both sides. And then I'm going to take the plus or minus square root. And so I've got plus or minus the square root of negative 3. So again, we've got that negative going on there. I know that's going to turn into an imaginary number. So this will become, and again, 3 is a prime number, so there's nothing else I can do with that. That will become my answer. Now, if I didn't see that there was only one term, I could use quadratic formula. It's just be a lot more involved to actually do that. So in this case, I think reversing operations would be a much better method. So again, our strategy there was use your discriminant, b squared minus 4ac, to determine whether it's factorable, or if the quadratic formula would be more appropriate. We only are going to use that, though, if we have an x squared and an x term. If we're missing one or the other, then we're just going to use reversing operations.